So, good afternoon, everyone. We are starting a new series of seminars called the Radio Astronomy Techniques Seminars, RATeS. Since this is the first inaugural talk, let me say a couple of words to introduce this series to you. So, as we all know, we are witnessing almost an explosion of radio data and spectacular radio images coming in from the new telescopes which have been operational in the past few years, basically the precursors and the pathfinders of the Square Kilometre Array. So this has driven several innovations in radio astronomy techniques, and basically this seminar aims to introduce these innovations and discuss possible solutions to the challenges in the road to realizing the full potential of the SKA. It is my pleasure to welcome our first speaker of this series, distinguished Professor Oleg Smirnov, to give a short introduction of him. He is an expert in the field of radio astronomical data processing, calibration, and imaging. He did his PhD in astronomy at the Lebedev Physical Institute of the Russian Academy of Sciences. And then he spent about a little more than a decade at the Netherlands Institute for Radio Astronomy, Astron as we know it. And since the past decade or so, he has been involved. He's been at South Africa, where he holds the research chair in radio astronomy techniques and technologies at Rhodes University, and leads the radio astronomy research group at the South African Radio Astronomical Observatory. So we are here today to listen about the adventures on the time frontier. So over to you, Oleg.
Okay, thank you very much. Am I coming through okay?
Yes.
Okay, great. Well, thanks very much for having me. It's an honor and a pleasure to open the series. And I'd like to say I've got 3 screens in front of me, and the chat window is on one of those screens. So if you have any urgent questions for me during the talk, I will actually see them come up in chat. So please feel free. I find it better when talks are a bit more interactive than just talking into a camera for an hour. Before I start the talk itself, I just wanted to show you a couple of fresh photographs of what we're up to this week. So I'm actually in Mauritius with a couple of colleagues, and we have been busy assembling a little miniature radio telescope. So you've got some photographs here of this going on. So you can see I don't just do imaging, I can also drill holes pretty well. And here is a picture of what we got to by this point. So you can see all the structures in place. It looks exactly like an SKA with one big advantage. Well, it's a smaller version of the SKA, and it's got one advantage that it actually exists. Although we haven't put antennas up yet, but I think that's going to start happening today. And if you're interested in this project, there is a link up on top of the slide there. You can get some details about the telescope. It's a super low cost 28-element radio interferometer developed at the University of Otago. It's so low cost that pretty much anyone can build it on any roof. So I would recommend that you try it. Anyway, now let me get to my normal subject. So this talk, at least the first part of this talk, is a little bit of an adventure story. And like all good adventure stories, it starts with a bit of a barmy idea. Now, when I talk about this live, I usually give the audience a challenge. Can you identify this object? Because radio astronomers usually can't. It's kind of hard to entertain guesses in an online version like this, but if you can guess what the subject is, put it in chat or just pat yourself on the back if you guess correctly. It's not a typical object for radio astronomers to study. What it actually is, it's Callista. It's a Jovian moon. And the barmy idea that a colleague brought to me at SARAO was to try to detect OH on Callista. The reasoning is, so Callista is expected to have a very tenuous atmosphere. It's predicted that there is some water ice on the surface, although it hasn't been detected by Galileo. So if you've got water ice on the surface, then it's going to get knocked out by UV photons. It's going to disassociate into H and OH. And then you can expect some pumping mechanisms to actually produce maser emission. So you can have a maser line from the atmosphere of the moon. And with some optimistic assumptions, some people who understand this better than me did some modeling. And we saw that with MeerKAT sensitivity, it's quite possibly detectable. And that was a kind of a very cool idea, because if this is possible, then it's a completely new way to probe for water on icy moons. And it's not even such a crazy idea, right? Because this actual detection of mazed OH emission has been made in comets when studying comets with single dish telescopes. So it's not completely crazy. The crazy part about it is that comets don't normally sit next to Jupiter. I mean, there was one famous case, but it didn't last. And Jupiter is a big fat radio source. So there were some concerns whether we can even image Jupiter well enough to disentangle the emission from Jupiter from the emission from Callisto. And turned out we had some science verification observations of Jupiter sitting in archive. I didn't even know about this. Neeraj, actually, if Neeraj is online, Neeraj took those observations while he was still with SARAO, but they were sitting in archive unprocessed. So we thought, right, well, let's, before we do Callisto, let's just process some Jupiter data just to see if we can image it well enough, see if we can overcome the imaging challenges. And turns out there was one of the observations was actually done during the Great Conjunction of 2020 when Jupiter was next to Saturn. So, of course, imaging Jupiter, it's, well, Jupiter is a bit of a problem child for interferometry. As you know, when you do conventional aperture synthesis, you kind of assume that your subject is sitting still during the multiple hours that you accumulate data. That's kind of our fundamental assumption in Fourier imaging. And Jupiter is like a child or like a puppy. It doesn't do that at all. It actually, well, first of all, it's moving with respect to the background sky quite appreciably. It's a planet after all. And second, as it turns out, it's got these very bright radiation belts which tilt and rotate as the planet moves along. And they tilt quite quickly because the period of Jupiter is about 10 hours. So over several hours of observing, you are going to see the belts go back and forth. So I'll have an animation of this a little bit later. So for this observation, Jupiter is kind of like a beautiful nuisance, but it turns out there are people who are very interested in the radiation belts themselves. So this scientifically was quite interesting too, this observation, and there's going to be a paper coming out about it shortly. Now, how do we process such an observation? It's a bit of an unusual observation for a radio telescope, right? Because instead of tracking one spot in the sky, we are tracking a moving object. So through the observation, MeerKAT points at Jupiter, follows Jupiter, and this is interspersed with kind of normal calibrator scans for the phase calibrator. So the telescope is basically going calibrator, sits still, then goes to Jupiter, follows Jupiter, then goes back to calibrator. So initial calibration is exactly the same as for a normal observation, because at least your calibrator is sitting still. So you do the normal bandpass, gain calibration, transfer resolutions across. And then you start imaging, and you kind of assumed, well, we'll just start doing self-cal, and self-cal will sort everything out as it usually does. But of course, Jupiter, like I said, it's bright, it's variable, there's moving sources in the field. So we said, right, let's do self-cal, let's do imaging individually per each scan. One scan is about 15 minutes, so let's process each scan independently. And I show you here 3 examples. These are the images after initial calibration of 3 scans, the 3 initial scans. I call them the good, the bad, and the ugly. And in the good one, you can just about see that there's Jupiter sitting there in the middle. At least you can see it's a planet or something vaguely Jupiter-shaped. In the bad scan and in the ugly scan, not so much at all. And looking at this, you might ask, well, why does the ugly actually looks not as ugly as the bad one does? But this is because what's going to happen after self-cal. So I'll show you what happens with self-cal with the good scan. So you start with your initially calibrated image, then you start doing self-cal. Turns out you have to proceed slowly because it's such a bright object. So we do 3 rounds of phase and delay self-cal. The slide says delay, but that's actually it's phase and delay that's being calibrated for. And after 3 rounds, things begin to converge. And you get this image of Jupiter of one scan. And then you can do a DDE solution because there's a bright off-axis source as well. And you get a somewhat reasonable image. So that was the first scan I processed. I thought, okay, this is great. I can apply this procedure to all the other scans. And this is what happened to the bad scan. The bad scan was not so bad after all. It started bad, but after a bit of like the intermediate self-cal images had this ugly negative ball in them, but after 3 rounds, it converged to something nice and GE solutions worked again. So great, we go on to the next scan, and this is the ugly scan, and this is what happens here. So here you try doing self-cal, and it converges to nowhere. Well, at least to this, which you will agree doesn't look like Jupiter at all. So this was kind of very puzzling for a while, and I was really stumped for a bit. And then my colleague London actually reminded me of my own rule or my own joke. This is kind of a joke I've had in my old talks for years and years. You may not be interested in the polarization, but the polarization is interested in you. So this is actually a misquote. It's supposed to have been said by Trotsky about revolution. I actually Googled this. Turns out Trotsky never said any such thing. It was something that was made up much later by other people. So he didn't say it about revolution. He didn't say it about polarization, certainly. He should have said it about polarization because it's actually true. And it's a good rule to not forget. So what's happening here is because Jupiter itself is highly polarized, and we start self-cal with a polarization independent model. So there's a lot of Q, but we haven't got that in a model. But now we're solving for X and Y delays independently on the telescope. And all that unmodeled Q, you know, in a measurement equation, Q appears on diagonal terms, so it appears in a parallelogram correlations. All that unmodeled Q ends up being absorbed into the gain solutions because we haven't got it in the sky model initially. And this was the reason why some scans do not converge. And well, fortunately, it turned out to be simple to overcome. So I was using this lovely calibration package called Cubicle, which Jonathan Kenyon wrote. And he quickly added what we call the unislope solver to Cubicle, which basically solves for a single delay for X and Y together. And that, while the phase offsets, we still treat independently. And that pretty much solved the problem. So I can show you what happened to, this was the ugly scan before we tried this approach. And then as soon as we went with this approach, the ugly scan also converged to something very sensible, a nice image of Jupiter. And the last thing left to worry about was these spokes. I don't know if you can see them on Zoom well, but there's these faint radial spokes emanating from Jupiter, which no amount of self-calibration could get rid of. And for comparison, you can see that these spokes actually show up in all the scans, not just an ugly scan. And turns out, again, this was, I won't take credit, somebody gave me the idea. They said, well, what if Jupiter is more variable than 15 minutes? We're treating 15 minutes as a static imaging problem, but what if there is strong variation below 15 minutes? Turns out this was something very easy to check for, right? If you use WS clean, it's got this parameter called intervals out, which basically says, right, I want to take my data, I want to split it into 4 chunks in this case. So 4 chunks of roughly 4 minutes each. And then it images and deconvolves each chunk independently. And you can see in the slide, I'm showing you the per chunk images, the 4 per chunk images. And they are, of course, noisier because each one uses a quarter of the data. But once we deconvolve them independently and then average them together, we get an image for the scan that has no spokes. So this basically proves that Jupiter, well, the radiation belts of Jupiter are sufficiently variable at minute timescales to actually, with MeerKAT sensitivity, to screw up the imaging. Which is interesting by itself, because people who study Jupiter didn't know that the belts vary so rapidly. So this is something else that's going to be very interesting to look into. And here you can see just a blow up of the image before and after these 4-minute solutions. You can see the spokes go away nicely. And finally, basically, once we've processed all the scans, what we can do is we can make a movie of, there are 27 scans in this observation. So here's a movie of the 27 scans following one another. I recommend you follow the link on this slide or follow the QR code, because Zoom really does this animation no justice. It's far better to watch the original version. And I call this image Astronomer's Bingo because it's a fun game to show this to an actual astronomer and ask them how many interesting objects they can identify in this image. And especially to optical astronomers, they really get lost, right? And you can have them puzzle over this movie for half an hour, and then they're very embarrassed when they finally figure it out. So it's a fun game to play with astronomers. Again, online talk, I can't really play this game with you, so I'll just have to tell you what you see here. So in the middle, you see Jupiter. So as I said before, the telescope is following Jupiter, so all the other background sources are panning past. Except if you've got sharp eyes, you can spot Saturn. You can see that Saturn, there's one object that's not following the rest of the sky, that's kind of trailing a little bit. And that is Saturn. Over here in the bottom left and the bottom right corner, you've got a zoom of the central region. So in this one, you see Jupiter and Saturn. In this one, you see Jupiter itself. We have polarization data as well, like I said. So we can use that to plot the magnetic field vectors. And you can see that it's like it's almost a perfect, well, it's a perfect little magnetic dipole. It's like those magnetic contours are so perfect, they're almost boring. And you can see because they, so it's got a 10-hour rotation. This movie is about 9 hours in length. So over almost a full period of rotation, the tilted magnetic axis causes its magnetosphere to kind of boom around. Well, this is what drives the radiation belts in the first place, this mechanism, giving you this nice tilted barbell pattern. You can also see some radio galaxies showing up. So, you know, again, I was having a quiet laugh at optical astronomers. You know, they were looking at the conjunction because there were two pretty planets together. But if you're a radio astronomer, it's not just two pretty planets in a conjunction. It's also a couple of FR2s, you know, supermassive black holes showing up. There's a particularly beautiful FR2 floating at the top here. Another neat thing was that we could actually detect Callisto itself in this observation. Not in one frame. In one frame, the signal to noise is not high enough to see Callisto. But if I take an average of 5 frames, which you see here at the top, it's basically a five scan sliding average, you can see a little faint dot moving in the middle, and that's exactly where Callisto, you can see from the ephemeris that that's where Callisto is supposed to be, and that's exactly where we detect a little faint moving point source, which is very neat because it's purely thermal, and it's like 120 degrees Kelvin. It's a ball of rock at 120 degrees Kelvin, and we can detect it in thermal with MeerKAT. But the biggest surprise about this observation was, I'm sure you've noticed by now, if you look in this circle here, at the start of the animation, there's something that goes off. So we looked at this long and hard, and we realized it's an actual transient source. So our conjunction got even better. We also had an unexpected transient show up. It lasted for about 45 minutes, then it went away. And that's kind of where the second part of the adventure started. Before I go there, I will show you another way to look at that same data set. So instead of making a movie, what we can do is we can make those 27 frames, and we can mosaic them in the image plane using standard tools like Montage. I used Montage for this. And this is quite nice, right? Because now this looks like a typical deep MeerKAT map. So you see some beautiful radio galaxies in the image. And here's the two that showed up for the conjunction. And these two long smear tracks, which look like sausage, which is why I'm calling this the worst case pipeline, worst being the South African term for sausage. So these two sausages are Jupiter and Saturn. That's how far they've moved in the sky over 9 hours. And the amazing thing is that in retrospect, you can actually, well, I don't think you can see it on Zoom, but I can see it on my screen. Right here, there is a little point source where our transient showed up. But this I only found out later when I started looking for it. Another thing you can do if you've got a transient source and you still got the visibilities, you can form up what we call dynamic spectra. So you add all the visibilities phased on the position of the source, and you end up with plots like these. So these show you the time frequency behavior of the source during the observation. So time is along the horizontal axis, frequency is along the vertical axis. So that's the MeerKAT L band. And you've got Stokes I, Q, U, and V plotted. You can kind of see the uneven sensitivity across the band. That's because of flagging, because of RFI. So the sensitivity jumps. But you can, and the gaps in time are, of course, the calibrator visits. So each one of these blocks is one single target scan. And you can see where this thing turns on. It turns on, it's quite broadband, it's highly polarized. In fact, it's 100% polarized, as it turns out. It kind of switches on, it's really bright for 15 minutes, and then for the next 30 minutes, there's kind of an afterglow, which is more narrow band, and then the thing disappears. So the other thing we could tell from this was we could get a rotation measure, because if you look at the Q and U signal, you can see a clear rotation between Q and U across frequency. So we can fit a rotation measure to that, and from the rotation measure we can, well, basically the one thing we found is that it was consistent with the galactic rotation measure in the Opperman map. There's actually an updated map that's a follow-on to Opperman. But anyway, the rotation measure value is consistent with galactic, and galactic latitude is -27, so a bit high for a galactic object, but not unreasonable. So of course, after this, well, for myself, I forgot about Callisto because it seemed much more exciting to go look for this transient and find out what it was. So we got some follow-up time on MeerKAT, and this is what it looks like. So this is now a more conventional observation, just kind of a deep pointing at the suspected location of the transient. So you're seeing here a deep UHF map with MeerKAT. You know, you will recognize all the radio galaxies that you saw in the animation. Here is a zoom of the central region, and the position of the transient is circled. So in the deep follow-ups, we could quite reliably see a point source at that location. And if you split the data up in time with various cadences, we could tell that the point source was variable. And it was varying by a factor of like 10 or 20 in some cases. So 45 minutes is actually a very funny time for a transient to be on for, right? You know, they tend to be either, variability tends to be either on much longer time scale or on much shorter ones. 45 minutes is funny. So we puzzled for quite a bit about what this could be, and in fact our working theory for a while was that it was a brown dwarf and that we were watching a brown dwarf flare. The project is still called the Brown Dwarf Mining Company, or at least the repository is called that, reflecting that old theory. But all of that went out the window when, during one of the follow-up observations, the MeerKAT commensal search engine, which, you know, whenever MeerKAT is observing whatever it is observing, MeerKAT is running and is looking for fast radio bursts and pulses in the beams that it forms up in the sky, completely independently of the correlator. So the MeerKAT people emailed us saying, oh, you're detecting pulses in one of your observations. And of course, they detect pulses in their coherent beam, which is relatively large compared to this image resolution. So they could not localize the pulses, but by matching timestamps to our images or to our snapshot images, I could tell that our source was brightening exactly when they were detecting pulses. So after that, finally, the penny dropped. We realized, okay, we're dealing with some kind of pulsar or possibly an RATeS. After that, we did one follow-up observation in UHF where we had the full pulsar timing engine switched on. And I'll show you the results of that now. They're really quite wonderful. This is basically this is a summary of all the observations we eventually got on the source, 4 in ELBA and 4 in UHF. And what this basically shows you is how bright the source was getting in some of these observations. So this column shows you the mean flux of the point source we see at that position. And the peak shows you the maximum brightness we recovered in the snapshot images. So you can see that it was like in each observation, it was variable and it was boosting by a factor of, reliably by a factor of 10. And in that first observation, when it was next to Jupiter, it actually boosted by almost a factor of 100, which is also quite a bit unusual. So I'll get to that in a bit. This is what the detection looked like when MeerKAT detected pulses. You can see this is kind of plots that MeerKAT produces. Again, these are dynamic spectra, time and frequency, except at much higher resolution. So this is sort of resolution the timing engine gets. And you can see this nicely dispersed pulse, which then they do the dispersion to get a dispersion measure. Turns out to be a very low dispersion measure, unusually low, which is perhaps why they were missing it in the initial observations, because for some, they have a filter for very low dispersion measures in the search engine. They tend to look for more dispersed objects. And then once we have the full pulsar timing engine on, we can get quite detailed dynamic spectra from the pulsar timing engine, right? Again, this is very high time frequency resolution. Each one of these plots is a dynamic spectrum for one scan on the object. In this case, it's a more conventional observation. So a scan lasts for about an hour. So you've got about an hour of data across in each plot. And this is I'm sorry about the labels on the frequency axis. It's not actually frequency, it's channel number, but this is UHF band. So this is from 588 megahertz up to 1100 roughly. So this is basically showing you what the pulses look like when they are received. And you see this wonderful behavior with like little peaks and bursts and arcs and all this frequency structure. And actually, I didn't know anything about this, not being a pulsar person, but it was explained to me that I am ignorant and I should have known it. What this is scintillation, right? So because pulsars are very compact objects, they will scintillate in the interstellar medium, and that can cause variability, and it causes precisely this kind of behavior because scintillation, scattering in the interstellar medium, is a very chromatic effect. So you have this very very large variation in frequency of this effect. Now, the strange thing about this object is that, I mean, scintillating pulsars are not unusual, but watching something scintillate and completely change the character of its scintillation from hour to hour, that's a bit unusual. The fact that these scintillation characteristics completely change, that's what makes it a very strange pulsar. And for reference, here is this is the first 5 hours of that final observation. Here is the last 4 hours, and you can see this very strange behavior continues. So that's the pulsar engine. Now, what about imaging? So when you observe in this mode with the pulsar engine on, you're getting two completely independent data streams out of your instrument, right? You have your timing engine data, which is, so it forms a coherent beam on the source and gives you very high time resolution data, which I was showing in the previous slide. But at the same time, the correlator is on, so you're getting visibilities. We're getting at a lower resolution, much lower time resolution, 8 seconds in this case, and only for 1,000 channels. But those visibilities correspond to the full field of view. So what we can do with the visibility is we can make a deep image of the full field. Then what we do is we deconvolve and we subtract the most complete sky model we can. So we're trying to subtract all the visibilities that correspond to everything that's completely static in the image. And then we can do two things. So we can do, either we can make very high cadence, basically 8-second snapshot images, and then we can measure a light curve. Basically for every pixel in the sky, every pixel of interest, we can measure a light curve. And this way this is a relatively cheap operation. So in practice, this adds, let's say self-calibrating this image, and the imaging takes several hours. Well, if you want to get light curves, it's going to be several more hours. Factor of 2 increase in processing time. The other thing you can do with visibility is you can build dynamic spectra. So you do a rephasing operation, you rephase all your visibilities to a direction of interest, and then you add them up and you form dynamic spectrum. This is quite an expensive operation, so you can only do it for, well, it's reasonable to do it for several chosen directions, not for the whole field at once. But fundamentally, when you do this sort of data processing, fundamentally you're measuring the same thing. So you can compare the results and you can hope that your results are consistent. Ruto, by the way, I didn't ask how much time do I have? Is it an hour for the whole?
You have,
the whole talk?
Yeah, you have about 20 minutes.
Okay. So I can show you a comparison. So here's a comparison of what we get when we make dynamic spectra from visibilities. That's at the top here. And this is at the raw time frequency resolution. And then we can do a bit of Gaussian smoothing or some fancier smoothing on the signal. So this is the kind of dynamic spectrum we get from the visibilities. And if you compare it to the dynamic spectrum from the pulsar timing engine, basically here you see 5 blocks in this spectrum, 1, 2, 3, 4, 5. That's the 5 scans. Here they're arranged as 1, 2, 3, and then 4 and 5 at the bottom. And if you compare these blocks, you will see that we are picking up largely the same structures in the two dynamic spectra, which is not surprising. It just means the timing engine was operating correctly and we formed up the dynamic spectrum correctly. Of course, the timing engine gives you much better detail. This is not surprising. But the advantage of the dynamic spectrum from visibilities, is that you can do this for any source in your field. You can go to the MeerKAT archive, pull out an observation, and you can make a dynamic spectrum like this for a source if you wanted to look at it. Whereas the pulsar timing engine, well, you had to have it on and you had to have it pointed at your source. If you didn't get that data, you will never get it without reobserving. So these dynamic spectrum from visibility is less detail, less signal to noise, but available hypothetically for any source that MeerKAT has ever observed. And here's a comparison with the light curves. So here I'm showing you the dynamic spectra and the light curve we get from snapshot images. So effectively, in a sense, a light curve is basically a dynamic spectrum where the frequency axis has been collapsed. So it's like a broadband flux measurement. And this is what you can see for the Jupiter event. The bottom plot with the light curves, this actually includes error bars. They're just small. So you can see it's really quite large in terms of sigmas, the amplification that was going on. Not surprising, it was a factor of 100. Here's a dynamic spectrum and a light curve for a follow-up observation. And now you can see that at the 8-second cadence, we don't actually see any boosting in the source, nor do we see anything in the dynamic spectrum. But if we smooth this thing in time to kind of focus on a slightly longer time scale of about 2 minutes, now you can see there are some events where the signal is popping up. And the color coding in the light curves here is anything above 4 sigma is plotted in red. So you can see we have quite a few 4 sigma excursions in the source. And if you look carefully, you'll find corresponding structures in the dynamic spectrum. And you will actually see that these events are quite chromatic. So in the light curve, they're a little bit suppressed by averaging across the band. And then same thing for another L-band observation. Again, the raw data doesn't show so much. You smooth the time curves, you get some nice peaks. And I think in our final UHF observation, this is the UHF observation where the pulses were originally detected, and they were detected here. I marked it by a green bar. So you can see we had a very nice excursion in the light curve when the pulses were detected. And here is our last UHF observation where we had the full timing engine. And here you can see the source really cooperated and went a little bit crazy on us, because you really see this very nice structure and dynamic spectra and the light curve. And if you smooth a bit in time, you see quite a lot of very strong things in the light curve. Now, of course, the all-important question is, what is it and why is it doing that? So I was very much hoping it would be, we could call it an RAT, because as you know, my research group is called RAT, for Radio Astronomy Techniques and Technologies. So I thought having an object called the RAT would be a lovely joke. Turns out Ben Stappers told me, no, I cannot call it an RAT, because we can see a point source in the images. RATs are supposed to like turn on and then disappear. So he says, no, if you can still see it, it's not an RAT. So I had to think of another name. Fortunately, we got an even better one, because, well, basically this is a highly scintillating pulsar, and it's clear that it's scintillating, but it's a bit difficult to explain the behavior in terms of ordinary scintillation. It's in the ecliptic plane. It's very close to the ecliptic, of course, since it showed up next to Jupiter in the first place. So we can expect a lot of interplanetary scintillation, but interplanetary scintillation tends to be very rapid and only a factor of like 1.5, not a factor of 10, not a factor of 100, and on a time scale of seconds, not tens of minutes. Interstellar scintillation tends to be a lot slower. It's, we're talking about weeks and months, although there are a couple of examples known of intraday variables. This is kind of almost an extreme intraday variable, this object. And of course, you think maybe the ionosphere, but the ionosphere, if there was something weird going on with the ionosphere, it would also affect the other sources in the field, and we see nothing like that. So we've got the paper out. If you follow this link, you can see the paper, but the paper basically raises more questions than it answers. There's some weird ideas that because of the timescale of the behavior, the scattering screen has to be either quite close to us or quite close to the object. So either there's something weird in the environment of the pulsar, or there's something weird close to us that we haven't observed before. So some scattering screens on the Oort cloud. There was an aperitif result last year which suggested something like this is possible. I think Tom Osterler wrote that paper. The other idea was that maybe we were picking up radial filaments in a solar wind. So instead of the normal turbulence of the solar wind passing across the source, there's kind of a more coherent structure that almost lenses it. And the name of the source is a parrot. So it's a pulsar with abnormal refraction occurring on all odd timescales, which is a very pleasing name because the Rat and Parrot is a very famous pub next to Rhodes campus where Just Andronis, for example, probably spent 30 years, so it has a unique place in SK history, this pub. So in the end, I'm very pleased that it's not an error. I can call it the rat parrot instead. But what this highlights is, to me, it's, no, it's not just an object. To me, this highlights the capabilities of MeerKAT. And basically, we can turn MeerKAT into a light curve machine because, like I said, with only a factor of 2 increase in overall processing time, which is quite cheap, we can get, in that UHF observation, we're measuring 40,000 light curves simultaneously from a single point in a single field of view. And the sensitivity on this is just incredible, right? Our instantaneous sensitivity is well below 150 microjansky in those 8-second light curves. And that's something, so these timescales of variability at these flux levels have never been observed before with any other instrument. So we're really kind of probing new areas of the parameter space here. Still some problems to be addressed. So primary beam need to solve for that properly or correct for that properly. So you can see, I show you an example here. The light curve at the bottom looks like the source is varying nicely and smoothly, but actually it isn't. What this is the source sits on the flank of the primary beam, and as the sky rotates through the primary beam, there is a little variation on the order of, well, actually quite a bit in the source. So the source is going up and down in the sensitivity pattern. So we have to take care of that before we can automatically process these light curves. The other thing we can see quite well is interplanetary scintillation. And like I said, it acts on a much faster time scale. So you can see this on the top light curve. So all the red points are 4 sigma excursions with respect to the mean of the light curve. And there are actually error bars on this plot. They're just tiny. So this behavior is exactly what you would expect from normal interplanetary scintillation. This is the source being scattered by turbulence in a solar wind. It basically, its time scale is 1 second. So if you measure it at 8-second time slots, you're seeing the source basically jump up and down randomly in every time slot. And this sort of behavior we see consistently across the field. So it's also an idea to use this as a probe for, I actually say this on the next slide. We can use MeerKAT as a probe of interplanetary scintillation. One idea I had was kind of to try to recover structures on a solar wind from a wide field observation, which would be kind of fun because what I didn't realize is that the first pulsar discovered by Jocelyn Bell was discovered on a telescope called the Interplanetary Scintillation Array. They actually built that telescope to measure interplanetary scintillation and ended up discovering pulsars. And now we've kind of come full circle. We've found the pulsar, and now we're thinking, we should be measuring interplanetary scintillation. But what really got me focused on the problem was a talk by Ian Haywood, so credit to him for this. If you were at the MeerKAT at 5 meeting and saw his talk, you would have seen this idea. The idea is to, well, let's now build 2 robots, 2 automatic pipelines. And 1 robot can go forward in time. So if we can refine this procedure to the point where we can self-calibrate an image pretty much in real time, it's a bit ambitious, but I think it's within reach. Then potentially we can have a commensal transient detection engine on MeerKAT, right? So whatever MeerKAT is observing, try to watch for these kinds of objects in real time. So that's the robot going forward in time. At the same time, we can have another robot, or actually an army of robots, mining the MeerKAT archive, because we've got 6 years of data. We haven't looked at almost any of this data on these timescales. There's bound to be, tons of such objects in that data. So if we can build a mining pipeline and set it on archive, I'm sure we'll make a lot of wonderful discoveries. And that kind of neatly takes me to the second subject of my talk. These 2 robots are actually very different problems, right? The one robot needs to deal with data in real time, and that's a difficult problem algorithmically. It's a difficult problem for many reasons, but it's only the one data stream from MeerKAT, right? Because you observe data at the rate you observe data, not faster. The army of robots that deals with archive, that's a massively parallel problem. So you don't need a very efficient pipeline. You can do it with current tools because each chunk of data can be processed completely independently. It's embarrassingly parallel. So you can think of using something like the cloud to spin up, 1,000 instances and go mine the data. You're probably more limited by the rate at which you can pull data from the MeerKAT archive rather than computing. So it's a massively parallel problem, but I said the cloud, and now I pivot to the second part of my talk. Well, the fact is, we haven't really used the cloud in radio astronomy. And I got to wondering about this back in 2021 when there was this wonderful talk at ADAS. There's a link on the slide. You can go see a video of this talk by Frosi Economo, who built, well, not herself, but she played a leading part in building the Vera Rubin science platform. And they built it completely on the cloud using the Google Cloud Engine. It's not a small project. It's 100 petabytes of data that they're processing. And she was adamant that the cloud was the best solution for them. She says it's not cheap, but it's great value for money. And it's a no-brainer in terms of computing costs. And that argument kind of makes sense, right? Because there is absolutely no way you can provide computing power cheaper than Google, right? Or Amazon. It's just kind of an economy of scale argument. Even if you include the markup that they add to the compute power when they sell it to you, they can build huge data centers with a much lower unit cost than any one of us can in our university IT departments, right? So why aren't we using it? Why has it not worked for us? It's not for lack of trying. So in 2015, there was an SKA Amazon call for proposals for us to compute on the cloud. They were basically giving up free cloud time for people to do experiments with cloud computing. And I Googled, I found some reports, I found a little paper. So people tried some things. I remember we tried some things as well. Basically, we did some simulations and didn't get very far. But basically, I thought about, and I think the reason it hasn't worked is because if you use the cloud just as a way to spin up a virtual machine, which you treat as an extra compute node, then all you have is a compute node that's inconveniently located, and it's got a dollar meter attached to it, so you're paying by the hour. And people have tried the cloud, using the cloud in those ways, and it has never proved efficient for them. So I think this is why we were stuck. But at the same time, if you look at today, the data science community, the machine learning community, they use cloud computing in very novel ways and quite heavily. And we're not doing imaging, so why not? And I think that's because, well, why hasn't it worked for us? I think that's because the radio astronomy problem has a few unique features which make it awkward. So first of all, our data format is super awkward. So we still use the measurement set, and well, actually the measurement set is great, but it's a victim of its own success because the measurement set is 1990s software technology that was so successful that we're still using it in 2024. But in fact, it's really showing its age. It's ill adapted for parallel processing or even basic multi-threading. You cannot do multi-threaded applications on a Casa Core backend. And if you put it on the cloud, then you need a virtual file system volume, like what they call EBS in Amazon. It's not suitable for cheaper storage, such as object store, such as S3. So you really need to make a virtual file system, which is the most expensive storage there is in the cloud. The other problem, of course, is that our software is just so awkward, right? All the best MeerKAT images we make, the Jupiter movie I showed you, that was produced by heterogeneous pipelines, right? Using a combination of, Cubicle written in South Africa, WSClean written by Andre at Astron, and this just makes it difficult to deploy pipelines because you have to have many different pieces of software fit together. There's no end-to-end solution except Casa, but Casa doesn't do all the algorithm stuff that we need. And the final problem, I'll skip the red bits, but I want to comment on this final problem is that we've got our workflows are very thick and thin. So there are some steps in our workflows where we can go massively parallel, some parts of the imaging, and there's parts of the workflow where suddenly your problem is completely serial and you cannot exploit the parallelism. So if you allocate yourself a big multi-CPU machine in the cloud and run your workflows on it, half the time you're not using those CPUs because your workflow has gone parallel. But in the meantime, you're paying for a big multi-CPU machine by the hour. So it's just not very efficient to map our workflows into that kind of thing. And for that reason, it's very difficult to control costs, particularly if you're in a development environment and you're still experimenting. But this is all now changing a little bit. So there's a key piece of technology called Dask. And Dask, basically, it's a Python scientific computing library, which gives you arrays, which work like NumPy arrays. So you code for them like NumPy arrays. You say A equals B plus C, but what happens what happens in the language when you do A plus B plus C? It's not directly computed. Instead, it builds a graph for the computation, and then it evaluates that graph lazily on demand. And this has become very popular in the PyData community. Geoscientists use it a lot. If you know what you're doing, you can achieve HPC performance that's almost comparable with traditional C++ and MPI with Dask. And because basically Dask computes this graph of your computation and then evaluates it, the information about parallelism is encoded in the actual structure of the graph. So you can have clever schedulers that can take advantage of this information and actually automatically distribute and parallelize your compute. They will parallelize the graph and then do the computation. So you can kind of get parallelism for free without worrying too much about this. And Simon Perkins in my group in South Africa wrote this great piece of software called DaskMS, which was basically conceived as a Dask interface to the measurement set. And the idea is very simple. You attach your DaskMS object to a measurement set, and now it becomes visible as Dask arrays. And then you can write all your computations with the measurement set with the visibilities in terms of Dask array operations. And as actually it turns out, once you learn it, it's easier to use than traditional Casa core for working with data. So that's become the backend for a number of our software products. So Quarticle, the successor of Cubicle, uses DaskMS. PFB Clean, a new imager you'll be hearing about later this year, I'm sure, by Landman. Then we have a flagger, we have a visibility averager, we have visualizers. So actually, if you look at this lineup of tools, we've got most of the moving parts for a self-cal pipeline already in place using DaskMS. And a lot of the same ideas, if you look at NG Casa, they're also using Dask and even some bits of code from our tools. So this idea is really catching on. Now, the great thing about Dask, well, I'm really running out of time, so I should really hit the highlights. The great thing about Dask is now you can sort of start losing the measurement set. And this happened because when Jonathan wrote Quarticle, and Quarticle is the world's best calibration, the world's most parallel and efficient calibration package, what he found was that all his wonderful parallelism was going to waste because you couldn't read a measurement set fast enough. You could not read it in parallel. So, you know, his parallel code would basically sit there and wait for data to arrive from the measurement set. And this got him and Simon increasingly irritated. And then they had this brilliant idea. They said, well, we're already using DaskMS for the access to the measurement set layer. Why don't we dispense with the Casa core libraries, dispense with the Casa core table format, and swap in a more modern storage backend that can actually do parallel I/O. And they tried something called ZAR, and that worked wonderfully well. And they're now they're using also Apache Parquet, another open source technology that. And this is great because now you can replace the measurement set with something that's in ZAR format, and the application doesn't know about it. As far as Quarticle is concerned, it's still dealing with the traditional measurement set, but the backend is now highly parallel and allows for parallel I/O. And incidentally, what this also allows, the backend doesn't care if your storage lives on cheap object store. So suddenly with this development, almost for free, we got compatibility with cloud formats because we don't have to store these ZAR objects on a file system. They can be object store in an S3 bucket. And even better, well, I don't have a lot of time left, so I won't go into too many details, but you can do lovely things like dataset versioning and column caching with this technology. And basically, it's still completely invisible to the application programmer. The application programmer writes for DaskMS and deals with data that looks like a measurement set. On the back end, you can have all this magic working together. The other key piece that made it possible, that's making this possible now, so Amazon is offering free S3 storage for public datasets. So if you've got a dataset that's public, as is the case for any measurement set of MeerKAT that's gone public, you can apply. It's a fairly lightweight application process. Amazon will grant you free storage space. So this means if you want to put up a measurement set for the community to use to test their algorithms on, you don't have to pay for it, right? You can upload it and they will host it for free. And this kind of solved the problem of keeping testing data around, right? Because you're kind of afraid of developing an algorithm if you know you're going to pay for terabytes of data storage on Amazon while you develop. It'll just get quite expensive. But if that data is being stored for free, then suddenly our development costs are like a lot less. And the other key piece of the puzzle is something called Kubernetes, which is a new fairly new technology that was originally created by Google, but now it's an industry kind of open industry standard. And that's exactly what the Rubin Science Platform uses. So it's not just working on the cloud natively, it's using Kubernetes. And Kubernetes basically provides services for scheduling containers on compute nodes. And the way, I think I have a, rather than explain the technical details, I've got one diagram that shows why this works so well, particularly for a thick, thin workflows. So the way it works, it plays very nice with Dask, right? So if you have a Dask application with Kubernetes, and say you have a highly parallel application, so what happens is you've got your, you run the application on a very cheap, small virtual machine in the cloud, right? These are what's color-coded gray in this plot. These machine instances are cheap. And then the main application tells the scheduler, right, I can go super parallel. I can use 1,000 CPUs right now. And the scheduler says, right, okay, I'm going to bring up large, expensive virtual machines for you with many CPUs. You told me 1,000 CPUs. Here you go. Here is, let's say, 10 instances of 100 CPUs each. Go run. And the application then runs its worker pods on those expensive but very fast instances. So it goes massively parallel. And then when it's done, the autoscaler goes and destroys those expensive machines. And then if you've got a serial step in your pipeline, you're running on a cheap machine again. So this technology kind of, if you use it properly, it solves this thick-thin problem of where we basically, when we have something highly parallel, that's when we pay for big machines. And as soon as we go to serial processing, we can pay for very cheap instances. And putting it all together in the final minute, I'll just put a plug for something called Stimela, which grew out of a PhD project at Rhodes by Speciale Macatini. And Stimela basically is a way to wrap all our software, and not just our software, but software from third parties like WSClean, DigiFacet, wrap it into Docker images, Docker containers. And then Stimela is basically a framework for chaining these containers together and passing parameters between them. And actually, just yesterday, we released a complete next generation rewrite of this framework. You can find it on this website here. The important point is that the Parrot paper, which I gave you a link to earlier, actually published a complete set of reduction recipes. So the data for the Parrot was reduced with Stimela, and the recipes are linked in the paper. They're up on the website. So in principle, it's the idea of Stimela is that it's completely reproducible. As long as you have a machine big enough to run this reduction, you should be able to download this recipe and run it. And because it's using container images, you're sort of almost guaranteed that it's going to be bit for bit perfect copy of the same software that we used for the original reduction. And I'm not going to show you how recipes work. That's probably a different talk. But the great thing about Stimela is that it's at the state where it's now in a kind of a run anywhere kind of thing. So you can run it natively on your compute node. Then your administrator just gives you your compute node and you run a Stimela recipe. You can run it on Slurm. So if you've got a login on the Slurm cluster, then the same Stimela recipe, you just need to give it a separate configuration file which says, right, I want to deploy on this cluster and I want to use these kinds of nodes for my recipe. And the exact same recipe will work on Slurm. And we've got it to a state where the exact same recipe will work on Amazon using Kubernetes. So this is kind of really moving us towards truly reproducible data reduction stage. Because I kind of joke that on radio astronomy, we don't have a reproducibility crisis because nobody tries to reproduce anything, right? I mean, quite often I cannot reproduce my own images from half a year ago. But with this technology, I think we're finally moving to a state where we can hope to reproduce things. And one thing we hope to do in the near future, if you remember this wonderful radio galaxy that Patty published in 2020 with these strange threads linking the lobes of the galaxy. This is a really wonderful MeerKAT image and a wonderful imaging problem. So what we already have this data. The data is public, and we've already made it available on Amazon on the Open Data Program. And we're working on putting together a similar recipe, which goes all the way from the raw data all the way to the final image. And then we upload the recipe, and then we say, right, well, we're not going to have an image competition like people have been trying to have every now and then. Let's have a recipe competition. If you think you can make a better image from this data, well, take the recipe, replace the imaging step with your own step, and prove to us that you have a better imager, because a lot of people are trying to make better images. And then don't just publish a paper, publish data and recipes so other people can produce this thing. So I think that's basically it. That takes me to the end of my talk. I will leave you. I'm very bad at conclusions, so I'm just going to leave you with this animation again because it's so nice to look at. And thank you very much for listening.
Thank you, Oleg. We will take questions from the participants. So participants, please unmute and ask your question.
Or put it in chat or something.
Yeah, I don't see any. Yeah, if you would like to put your question, you could also put it on chat. Yeah, Vishwesh.
Yeah, I had a question on whether there is a VLBI mode of observing and whether you've thought about doing a VLBI experiment with other observatories, because at the GMRT we are trying to build our VLBI capability, and it'll be nice to try VLBI with MeerKAT.
Yeah, I agree. I agree. It would be very nice. As far as I know, there's no such capability yet, and I don't know that the observatory is working on it even, because there is a lot of focus is on the MeerKAT extension right now. As you know, MeerKAT is getting extra long baselines. So I don't think there is a VLBI functionality available anywhere in the near future, sadly.
Okay, thanks.
Yeah, Dharam, please go ahead.
Hi, Oleg. Nice talk. Thanks. One question is, this variable shows brown dwarf. Do they show circular polarization, the Stokes V also? Because I think the data.
Yeah.
I don't know. The object looks interesting. So.
It's correct. It's 11%. I had some here. It is. We can see some signal in V.
Yeah,
it's 11%.
Yeah.
Yeah, it's 11% polarized in V.
So
Yeah,
brown dwarf do show in general circular polarization. And what's the reason?
What, sorry?
So brown dwarfs do show circular polarization in general. And what could be the reason, like what kind of emission?
Well, I mean, in our case, it's not a brown dwarf, it's a pulsar. We thought it was a brown dwarf for that.
Okay, okay.
But the reason for this emission, so yeah, this is a bit it was a bit of an aha moment for me. So what's happening is, I think the pulsar is always pulsing at some ambient level, but because of this scintillation screen, there's some kind of lensing structures in the scintillation screen, which basically boost the signal every now and then. And what we're seeing in the images is basically the period of the pulsar is 1.6 seconds. So in every 8-second slice, we're seeing several periods, and we're seeing kind of the cumulative emission over the pulse. And that's what gives us the flux we're seeing in images. The mechanism is probably, well, I imagine it's a standard pulsar mechanism.
Okay, thanks. Thank you.
Okay, Arpan, please go ahead.
Hi. So just one thing to understand. So the commensal survey, when you guys like detected that transient in the image plane, say they got also some pulse detections, right? So
yeah.
We have any idea what is the typical width of that pulse? Like how they are like broad, like single pulses, right?
Yeah, they picked up a few, like 4 or 5 pulses during the whole observation. This was the pulses they picked up.
Okay. Yeah, so I just have another question. So as you mentioned that the steps that we do in the imaging are not like thick and thin problem kind of thing. Like some portions take longer time and some less. So let's say if I use your task space thing, the MS thing. Now, how much improvement do you are seeing, especially at the imaging step, like at the cleaning stage? How much improvement you are seeing, like a traditional doing a cleaning on a like normal CASA MS and using your MS?
You mean using our imager?
Yeah, yes.
Or well, when we're talking about the PFB imager of lambdas, I think what we're seeing now is a big improvement in image quality, particularly on extended emission. The performance is roughly comparable in terms of how much time it takes to take an image. Well, it's comparable to WSClean, and WSClean is a lot faster, usually much faster than CASA, I find. So it's faster than CASA. But the thick thin, solving the thick thin problem, it's not going to make your process faster. It just makes it cheaper, right? Because if you put it on the cloud, this means you don't need to run it on an expensive machine the whole time. You can do some steps on an expensive machine and some steps on a cheap machine. So it's not going to make it faster, but it does make it cheaper.
Okay.
Yeah, Ajay, do you want to ask a question?
Sorry, no, I got unmuted, I think, accidentally. Sorry.
Okay.
So,
Yeah, please go ahead.
hi, Oleg. Means how much time, how are you constructing the dynamic spectra from the visibilities?
So there's a tool by Cyril Tass that he made actually originally for LOFAR,
Yeah.
which constructs the dynamic spectra. There is a paper about to come out on this tool. We should look out for. It's an absolutely wonderful result they've got with LOFAR, right? They've got this emission from exoplanet hosting stellar systems. They show radio variability. That paper describes the tool, but to explain it in very simple terms, I mean, the principle is simple. You take all your visibilities, you apply a phase rotation. So now that your phase center is in the direction of interest.
Yeah.
And then for every time and frequency bin, you just add the visibilities of all the baselines together.
Okay.
So effectively, that's what the Fourier transform gives you for the center pixel. You're doing a Fourier transform and taking that center pixel. The trick is you have to apply the weights correctly, right? You have to reweigh your visibilities correctly. And the other big trick is noise estimation, because your noise is not just thermal, right? There is imaging artifacts, leftover DDA artifacts, which are buried in the noise. So he's got this whole thing for also forming dynamic spectra on empty positions in the sky and using those to make a noise estimator.
Okay. So in the paper means the construction of dynamic spectra is defined like this. Means firstly we form the image, and then from the image we extract the fluxes and then construct the dynamic spectra. In the Parrot paper, yeah.
No, not in the Parrot paper. In the upcoming paper by Cyril Tass, that's where the detailed description is. In the Parrot paper, we just reference it.
Okay. Yeah.
But
Thanks.
if you're interested, you could just email me or Cyril, and I'm happy to put you in touch.
Because we are also working on the same technique like what you just said, but in the paper I see the different technique. So I'm asking because that from constructing the dynamic spectrum from the image took a lot longer, like 10,000 times longer.
Oh, it shouldn't be 1,000 times. I mean, you only need to go through the visibilities once for each dynamic spectrum. So it shouldn't take, it might take an hour or two, but if it takes much longer than that, then something is not right.
Because we have to construct the image cube for the each time sample, and we have a lot of time sample there. Suppose it in a,
Yeah,
it
but
is
But basically, at the end of the day, you have to read all your visibilities from the measurement set, apply a phase factor to each visibility, and then add them.
No, yeah, that will take about like 5 minutes when we directly construct from the visibility. But when we are trying to construct it from the images, mean firstly convert the visibility to images, radio images, and then extract the dynamic spectra from the radio images.
Right. Okay. Yeah. Yes. Okay. But then you've got a huge data problem, right? Because if you make the
Yes.
images at sufficient time frequency resolution, you've got 4G cubes, and they're going to be huge.
Yes.
Yeah, that's a hard problem. I don't know how to solve that. We make light curves. The reason we make light curves and not light spectra is precisely because even adding a few frequency bands will cause the data problem to blow up, and then it doesn't fit in the memory anymore, and yeah, then it gets very, very hard.
Yeah. For that, I like 32 by 32 pixel only. Small region. Yes. Thanks.
Okay, is there any other question? Oleg, I had one question. So this commensal pipeline to actually image in real time, is this something possible in your future, or it's still in a?
Well, I promise you we're going to work on it, and I think it's possible. I've got a pretty good idea how to do it. But yeah,
Okay.
give us a year or two.
Okay. And regarding the MeerKAT archive, are the visibilities stored with all the, like, as they were recorded, or are they processed versions of the raw visibilities?
No, raw visibilities, completely raw.
Okay. Is the
the problem with the archive is that a lot of it is on tape, so
okay.
It's not yeah, all the observations are not so easy to get. You just have to wait for them to get restaged if you request them. But in principle, all the raw visibilities are available from the moment it was switched on.
Okay. And is the baseline dependent averaging done, or is it applicable to MeerKAT?
I think it's not done in archive.
Okay.
No, it is applicable to MeerKAT, yes. Very much so. You could get like a factor of 10 data reduction at least with MeerKAT.
Okay.
But of course, then they're not the raw visibilities anymore, because you have to, for BGA to be efficient and not to destroy information, you need to do at least initial calibration first and get the phases aligned. So we've toyed with these ideas of like, yeah, let's make a BGA averager and then at least average the calibration data, because it's 10% of the raw data. So in principle, it's a no-brainer.
Okay, thank you. One last question?
One question.
Okay, go ahead.
So, means the pipeline you are making, is it for the transient, right? So
Well,
means, is there any? Yeah. Okay, so is there any means specific transient we are looking for? Means like means how are we trying to find the transient? Means what specific property we are looking that we can tell it is a transient or not? Because basically everything means even the steady source fluctuates sometimes due to the atmospheric or instrumental effect.
exactly. Yes. That's yes, very good question. Thanks for that. Yeah, this is true. We need, and that's exactly what I've been actually struggling with the last week, looking for detection algorithms. Basically, yes, if you have a transient that's right next to an existing bright source, you're never going to be able to distinguish that signal from the source varying. As soon as you start making time cubes, which I'm sure you've tried to know, as soon as you start making time cubes, you see so much variation from existing things that you have to be very clever to find new to find actual transients. But if it's something that's, let's say 10 sigma above the noise, and if it's not right next to a bright source, then I'm pretty confident we can detect this. I mean, if you look at the parrot, it's very well detectable at 10 sigma, because luckily there's no bright source next to it.
Yes. Because already there are many efforts people put in finding the transient, means variable sources. Means, yeah, they can find the variable sources, but it is difficult to find the exact nature of those sources, means what they are. So they
Yeah,
are.
I agree with you.
Yes. So they are having difficulties, means sometimes the steady source also come as a transient as well because of instrumental effect like this. Yeah.
Yes, absolutely. Absolutely. It's not easy. But I'm at the stage where, like I said, particularly in the UHF observations, where this is exacerbated for us because of the ionosphere. At UHF, of course, it's worse. The time cubes look like a lot of garbage. Well, not a lot of garbage, but you see, well, sources are scintillating up and down because of interplanetary scintillation. They're jumping back and forth because of the ionosphere. There's all sorts of things going on. But I do have a heuristic algorithm that within all that, it detects my parrot and my parrot only. It doesn't pick up any of that other stuff. So it's tractable. I can promise you that if there is another parrot somewhere in the UHF field, we will certainly detect it.
Okay. Yeah. Thanks.
Okay, thank you very much. I think in the interest of time, we will stop here. We thank Oleg again for his time and very exciting results, and also some updates on various new methods of looking at data. So thank you very much, and we will conclude the session. Thank you. See you at the next
Thanks so much for having
RATeS
me.
talk.
Bye-bye. Thanks a lot.
Thank you.